Good evening, class. Good evening.
Good evening, teacher.
Right?
Hello,
Guy.
teacher.
Hello. Guy, please try to engage with me in the chat box if you don't want to talk. At least drop me a message. Say yes, no, so that I can see more interaction from students. You know how it feels when you teach online and none of your students reply you. All right. All right, guy. Have you reviewed? Have you reviewed? Have you reviewed the lecture note from last week? Remember what we discussed and talked about last week? Some of you, I guess, might even forgot the topic that we discussed yesterday and last week. Some of you might not pay attention during the lecture last week, so you don't remember at all what we discussed last week. Guys, today is week 12. So we spent, including this week, 12 weeks to discuss, to review statistical review. We only discuss econometric issue for cross-sectional data. Again, we spent 12 weeks to discuss econometric model for multiple linear regression with cross-sectional data. We mostly cover the topic which both dependent and dependent variable are quantitative, contain quantitative information. Last week, we discussed a topic on, remember, multiple regression analysis with qualitative information, right? So let me briefly recap what we discussed last week. Last week, we can divide it into two main headings. The first heading is when we talk about a predictor, one of your independent variable contain qualitative information. All right, we start with a predictor is a qualitative variable. If one of your independent variable contain qualitative information, there are two cases. The first case, if your independent variable contain two categories, all right? If your independent contain two categories, convert it to dummy variable. What is dummy variable? 1, 0 variable. 0 is the base group. For instance, gender, male equal 1, female equal 0. Or female equal 1, male equal 0. All right? If you have a predictor contain two categories, convert it into a dummy variable. And how you interpret it? No longer how much it increase, how much independent variable increase, change in Y. Here is more on comparison, right? Comparing to the base group, how much your group that equal 1 higher than the base group. For instance, when you run regression based on gender, you say if your base group is female and your group of interest is male, you say how much male earns higher than women. All right? Not if gender increases by 1 unit, how much it change on Y. No. All right? So if you have an independent variable contains two categories, convert into dummy variable. This is the first case, right? The second case, when you have your independent variable contains more than two categories, or it is an ordinal variable that contains more than two categories. In this case, you also need to convert those variables into multiple dummy variable. If it is three categories, you can generate it into three dummy variables, but you include in regressions only two dummy. All right. If there are three dummy, you can create three dummy, but include in the regression two dummy only. The one that you leave out, it becomes the best category. It becomes a reference category. So when you want to make an interpretation, always compare to best category. I told you that how to generate dummy using stata, either manually or using XI command. I also told you that if you use manually, you can decide on reference category. We have a hand-on exercise on stata on that. But if you use XI command, stata will decide for you. By stata default, they will remove the first category out. If you don't remember that, have a look at the handout. Remember that? All right, again, the rule I said is if your independent variable contains more than two categories, how many dummy to be included in the regression decided by number of category minus 1. If you have 4 categories, include 3 dummy. If you have 5 categories, include 4 dummy. So the rule is number of category minus 1 to be included in your regression model. All right? So this is the two cases when your independent variables contain qualitative information. Another one is, what if your dependent, your Y, contain qualitative information? Last week, guys, we only cover a model that your dependent variable contain two categories only. All right? Unlike independent variable. Again, last week, our lecture only covered dependent variable contain two categories. If your dependent variable contain two categories, also convert it to dummy variable. And then you can run a simple linear regression. But we no longer call it multiple linear regression. What we call it? Remember that? Because our dependent variable is dummy 0, 1, it no longer called multiple linear regression. We call it linear probability model. And this linear probability model has different interpretations. We no longer say how much exchange affect Y. We say how much exchange affect the probability of Y getting 1. I give you an example of married women joining labor force. All right? An example is if married women education increased by 1 year, how much it affects probability joining labor force. Last week, I did not provide you hand-on exercise on linear probability model, but I believe you can do it. We only change from numerical dependent variable to dummy dependent variable. But remember, we no longer call it multiple linear regression, we call it linear probability model. Today, after lecture, I will give you a quick hand-on exercise on this linear probability model. All right. This is a quick recap, guys. Any questions from last week lecture? Thanks to worry. All right, at least I have a few of you, interact with me in the chat box. Guys, if you don't want to talk, just drop in the chat box. Any question, guys?
No question, sir.
All right, guys. Thank you. So, guys, as I said, including today, we are already in week 12. Week 12, everyone. We discuss only econometric model for cross-sectional data. For only cross-sectional data. Next week, we will cover a topic for basic model for time series. But this week, as you can see on the share screen, we are going to discuss about heteroskedasticity. Guys, remember what is heteroskedasticity? You don't have to answer me. Ask yourself. Do you remember what is heteroskedasticity is? Probably no, probably yes. What is heteroskedasticity? In multiple linear regressions, remember we have 5 main assumptions. Specifically, our concern is zero conditional mean. How to address zero conditional mean assumption? The only way for now for you guys as an undergraduate student is try to include more relevant model, variable as much as you can. All right. That is zero conditional mean assumption. Assumption number 5, homoskedasticity. Assumption number 5, homoskedasticity. What does that mean? Variance is not correlated with any of your independent variable. If variance is correlated with your independent variable, we call it heteroskedasticity. Remember, if your variance, regression variance is uncorrelated, not correlated with independent variable, we call it homoskedasticity. So today, we are going to discuss what should we do if assumption number 5 is violated. What if your regression variance is heteroskedastic, not homoskedasticity? So again, what do we really mean by heteroskedasticity? I just quickly tell you. We mean that variance is correlated with independent variable. Here is an example again. All right. This is the residual from your regressions, and income is an example of your independent variable. You can't just plot residual against your independent variable. So what you can you see here? The higher income, the respondent that have higher income have higher residual, right? So variance is just a sway of residual, right? Remember that. So here, as you can see, when respondents get higher income, they also have higher residual, meaning that the observation located quite far from the regression line, right? So this graphical illustrations tell you that what heteroskedasticity means. All right, your variance here is correlated with X. Why? The higher income, the higher residual. See, it is not constant. If it is constant, even though the income get higher, residual should be located around this line, right? Should be located around this line. That when we call it homoskedasticity. But when you look at this graph, it is not homoskedasticity because residual correlated with income. Higher income, higher residual. If it is homoskedastic, higher income, you still obtain similar residual. It should be get closer and closer to this line, which is similar to the respondent that have low income. But the graph here does not tell us that assumption number 5 is met. Instead, assumption number 5 is violated. Again, guys, this is what we call, what we mean by heteroskedasticity. Any question before we move on? Because our topic today is about heteroskedasticity. Make sure you understand what we really mean by heteroskedasticity. Why heteroskedasticity is important? Remember, I always tell you guys that as an empirical economist, we want to test hypothesis, right? We want to know, for instance, education affect weight or not. In order to know whether education affect weight or not, we need unbiased coefficient. We need unbiased standard error. All right. And if your variance is error, you obtain incorrect standard error. So your hypothesis testing is also wrong. So if assumption number 5 is violated, what happened? Coefficient is not affected, but your standard error is incorrect, right? So that is why today we discuss about heteroskedasticity. Any questions? If you still have blurred picture about heteroskedasticity, do ask now.
Hello, teacher.
Yep.
So, can you show us a little bit about the graph of homoskedasticity so that we can compare it?
I did not put it here, but what it said, the graph of heteroskedasticity is that here, if you look at this graph, the higher income, the residual get far away from the line, right? If the graph of homoskedasticity is that even though the respondent have higher income, the residual still get closer to the line. For instance, instead of located here, it should be located around here. All right. So it doesn't matter how much income you have. The residual should be get closer to this line. But here, when the respondent have higher income, the residual get far away from the line. So it's just an opposite only here. It's just an opposite from this graph only. So just the residual get closer to the line. So when the residual get...
So the graph is for heteroskedasticity, right, sir?
Right, right.
Okay, got it. Thank you.
If there is an homoskedasticity, if you plot like this, you will see that the residual get, around the line here, something like that, not somewhere here. All right, it should be get closer when respondents have low income or when respondents have high income. All right, the residual should be around here, not there. But if you look at here, the residual gets scattered when the income get higher. So that tells us that there is a heteroskedasticity. All right. So I zoom. So now let's move next then. So you have already learned about the consequence of heteroskedasticity before. You know that if there is a presence of heteroskedasticity, or if there is an heteroskedastic variant or standard error, your standard error that you obtain from regressions is biased or incorrect. All right. So here, the consequence of heteroskedasticity for OLS again. If there is a presence of heteroskedasticity, like we show in the graph, so the graph show about it's just the relationship of residual or variant with one of your independent variable. So it can be the relationship with any x. All right. The example just show only one. All right. So even though there is an presence of heteroskedasticity, OLS still produce unbiased, all right, unbiased coefficient. Coefficient is not affected. Your estimate is not affected. It doesn't have any effect on your R square either. It doesn't matter. But what it affects is the variant and standard error, OLS estimated. All right. The variant and standard error get affected. So in this case, if your model contains heteroskedasticity, you need to correct standard error. Guy, I don't think you remember it. Do you remember the variance for your estimate in normal OLS? No. Don't worry. Just take note of this equation. All right. So if your model contains heteroskedasticity, you need to use what we call heteroskedasticity robust standard error. All right. So in the past, heteroskedasticity is a concern. You know, economists have to do a lot of job to produce heteroskedasticity robust standard error. But right now, the modern software can correct it easily. I will tell you next. All right. So if your model contains heteroskedasticity, normally with large sample size, it is not a really problem. But if your sample is small, if the sample is small, you have to do something with your standard error. So in most of the case, you have to correct your standard error. You have to produce standard, the heteroskedasticity robust standard error. And how to produce it? This is an equation. Variance of your estimate, right? Variance of your coefficient equal summation of I equal 1 to n r ij square u I hat square divided by SSR. What is R here? R here is the square residual. R square here is the R square residual from your original regressions. How about the use hat square here? This is the residual from a regression of xj that correlated with residual on all other explanatory variable. Right? And this SSJ RJ here, if you have a look at the previous, we have looked at this before. This is the sum of square residual from this regression. The regression that xj on other independent variable. All right? This is the formulation that you have to use to construct heteroskedastic robust standard error, or in short, we call it robust standard error. And sometimes it's also called here, as you can see, Y or Ecker standard error. But in simple, we can call it robust standard error. Normally, you call it standard error when there is no heteroskedasticity. But when there is a heteroskedasticity, you use this formula to construct a robust standard error. Now let's have a look at an example. All right. We have our weight equation. We use log weight. We run log weight on educations. experience, and experience sphere. All right. Usually, as you see, this number here, this is the coefficient. All right. This number here is standard error. No more standard error. The number at the bottom here, we call it robust standard error. After we correct it for heteroskedasticity. All right. Now, guys, you might see that this is, if you compare the standard error of the education, for instance, you may see that this is a small change only, but this small change is very important, right? Because you remember to say whether education significantly affects weight or not, you need to construct t-statistic, and that's t-statistic equal coefficient divided by standard error. If you use incorrect standard error, you obtain different t-statistic, hence you obtain a wrong p-value. So you make a wrong conclusions. All right. So here, the number that's highlighted right here, we call it heteroskedasticity robust standard error. It may be larger or smaller than their non-robust counterpart. All right. The difference are often small in practice. But normally, if you know that your model contains heteroskedasticity, you have to use robust standard error. You may ask, like, how do I know my model contains heteroskedasticity? How do I know the variant from the model is heteroskedastic? Guys, we will discuss statistical tests in a few slides. All right. But here, we start with how you produce robust standard error. All right. If I run it normally based on these equations, by the way, guys, I upload the data in the data folder for this equation. You have weight 1 data. I already uploaded weight 1 data. If you run weight 1 data, we will get back to that later. As you can see the screen here, I simply run regress, log weight, education, experience, and experience sphere. All right. All independent variable, education, experience sphere are all significantly affect weight. Right. Here, we use non-robust standard error. So how to produce the robust standard error that meet this equation? In Stata, it's very simple, guys. In the modern software, it's very simple. You run the same equation. Regress, log weight, education, experience sphere, comma, VCE robust. Then you obtain here, if you look at the earlier regressions, it only say standard error. See the red highlight here. All right. After you add an options, VCE robust or simply robust, now you obtain robust standard error. Very simple, very easy. Right? If your model contains heteroskedasticity, if assumption number 5 is violated, use robust standard error. And normally, guys, I would say, normally, the model often contains heteroskedastic variant. It often that your variance from the model or residual correlated with your independent variable. All right, the win. This is how we address the heteroskedasticity. Simply use VCE robust. All right, that's how we address the issue.
Because we see robust, it correct the variant, right?
Yes, it correct the variant and hence it correct our standard error.
Okay, thank you.
right? Very simple. But before we move on to this application, you need to understand the story behind it a little bit. Any questions? Can you follow me? Very simple. The idea is just, up to here, we only need two statements. First, you need to know whether your model contain heteroskedasticity or not. If yes, use this extension. VC is robust. That will solve the issue. All right, guys. In fact, in reality, the way you address heteroskedasticity is more than that. But I decided to take you only this option. In fact, I should introduce you to what we call weight least square regression. General what? I have a feasible generalized least square regression, something like that. There are a different model that you need to do as well to construct robust standard error. All right. Either you can use just simply this robust or you use another regression. But again, I don't want to take you so many things. So you don't know, you don't know what are you going to do. So for this course, just use this robust. But just for your information, there is another way that you can address the whole heteroskedasticity. For instance, you can use weight least square, generalized least square. All right. This is just your information. All right. Question, guys? Again, for this application, for the example, the data is weight 1. I already uploaded in our data folder, guys. If you want to just quickly run this. Again, we will do a hand-on data shortly after the lecture. Questions? No. All right. Again, today I only teach you guys how to address heteroskedasticity by correcting standard error. In the future, for some of you who may wish to do some sort of economic related master or public policy, you may learn other methods, as I said earlier, least square regression or generalized least square. All right. Don't say, oh, I learned from my lecture that we should only correct standard error. This is just one way. All right. Next, the question is, when we want to correct standard error, we need to know, how do we know that our model contains heteroskedasticity? How do we know that our model violates assumptions number 5? How do we know that assumption of homoskedasticity or constraint variance is violated? We rely on statistical tests. So now let's discuss about testing for heteroskedasticity. Remember, guys, if your model contains heteroskedasticity, use robust standard error that I just shown earlier. But how do we know it? Let's have a look at testing for heteroskedasticity. All right. Before we move on, I just want to tell you that today you will learn 2 types of tests that you can detect for heteroskedasticity. We start with Bruce Paragon test. All right. We start with Bruce Paragon test. But remember, this is our assumption number 5. Variance is, and given any of the x, it should be constant. And for this test, Paragon test, the null hypothesis is that your variant is constant. Your variant is homoskedasticity. So, if you accept this hypothesis, it means that if you use this test and accept null hypothesis, your model produce homoskedastic variant. But if you reject this null hypothesis from Paragon test, it means you fail to accept null hypothesis. That means your regression model produce heteroskedastic variant. All right, let's go into the next slide. For Paragon test, guys, for Paragon test, all right, your regression model originally equal here y, all right, equal, for instance, delta 0 plus delta 1 x1 plus delta 1 x1 plus blah blah blah. You have delta k xk plus error term. This is your original model that you want to test. And that this Paragon test for heteroskedasticity, how the test is done, they simply regress your variant on your independent variable. All right. So this Paragon test simply regress your variant here. How can you obtain this variant? Basically, you run these regressions, the original regression, and then you get residuals, where residual, and you run this regression. You regress variant on your independent variable and see if you accept null hypothesis or reject null hypothesis from this Paragon test. Remember, the null hypothesis of Paragon test is that the coefficient of your independent variable on variant equals 0. But if any of your coefficient of x on variant here different from 0, meaning your model contains heteroskedasticity. So since this is what we call joint hypothesis testing, you will construct IF test or statistics. All right. If you don't understand this, that's okay. But the story is here. For Paragon test, you regress residual or variant residual sphere on your independent variable. Where did you get this residual sphere here? It's from your regression analysis. All right. For instance, all right, this is your original equations. You basically estimate the heteroskedasticity for housing price. The data house one, if I remember correctly, let me have a look. I already upload this data in the data folder. Let me have a look on the data name. If you want to have to do a quick analysis and compare with this right now, the data is yes, H prime 1. The equation, the result here is from the H prime 1. All right, this is the regression result. Load size, I don't remember this variable name. All right, this should be load size, square root, the size of the house, and number of bedroom. All right, this is the coefficient of H independent variable on your dependent of variable of interest. And this is the residual sphere, the residual sphere. All right, they run the regression using Paragon test. And this is the p-value of Paragon test, either F statistics or LM statistics. So when you see here, guys, when you see here is that this is the p-value from Paragon test. It indicates p-value equals 0.002. What does that mean? It means that you fail to accept null hypothesis of constraint variant. So what does it say? It said that this model about here contains heteroskedasticity. So to help you have a bigger picture, let me come here first. I will get back here. All right. Here, I use the data of house price 1, guy. House price 1. You regress, right? Try here your dependent variable, and this is 3 independent variable. After you run regressions, you run, for instance, the state I will teach you later, right? Is state heteroskedasticity. So you want to run to test for heteroskedasticity. This command here is the Bruce Paragon test. And this Bruce Paragon test null hypothesis is constant variant. But when we produce, we found that the p-value here is 0.01. So if that is the case, we reject the null hypothesis here. So the null hypothesis of constant variant is rejected. So what do we mean? We mean that we accept alternative hypothesis that this model contain non-constant variant, which is there is a presence of heteroskedasticity. So the table on this equation and the standard error here, right? This is basically from this two number, coefficient and standard error, and this is 0, 0, 2 here when they run Bruce Paragon test. This equation here. All right, this is the first model. I stop first. Let's see if you have any question, if you guys follow me. Can you follow me? Question, guy? Can you understand me? So the first part here is just your original regressions, right? The below part here, so the result of Bruce Paragon test. Look at p-value. If p-value is lower than, say, 0.05, it means that you reject null hypothesis. And the null hypothesis of Bruce Paragon test is that constant variant. Constant variant meaning homoskedasticity. But here we reject null hypothesis of constant variant or homoskedasticity. So it means that our original model here contains heteroskedasticity. So the standard error that we produce here is incorrect. This standard error is incorrect. Questions?
Hello, teacher.
Yep.
No, we reject null hypothesis. Mean that it is heteroskedasticity, right? No.
Yes. Yes. Because null hypothesis of God. Let me just notify. When I say hypothesis, I do not mean hypothesis of your independent here. I mean the null hypothesis of Bruce Paragon test. Don't be confused. In the previous lecture, we talk about hypothesis testing of your independent variable here. But here, we talk about hypothesis testing of Bruce Paragon test. And Bruce Paragon test aim to test the presence of heteroskedasticity. And this test, null hypothesis is constant variant, homoskedasticity. So here, since p-value is lower than 0.05, so you reject null hypothesis of constant variant. So it means that there is a heteroskedasticity in your model. So what I'm saying here is that this standard error here is incorrect. So what you have to do is you need to use robust standard error rather than non-robust standard error. Do I answer you? Was that Lee here or David? Do we answer your questions?
Teacher, may you explain why 0.0028 is heteroskedasticity?
Now, this 0.2 or 0.28 here is just two different value from Bruce Paragon test. So from proof Paragon test, you can either use I statistic to produce probability or LM statistic to produce probability. You can choose either one. But here we present both. But here is the p-value. This is the p-value. And you remember how you interpret p-value? You compare p-value with significant level. If p-value is lower than significant level, you reject null hypothesis. Right, Devin? So here, p-value is 0.002, or if you use this one, is 0.0028. Meaning that this is lower than significant level. If it's lower than significant level, what did you say to null hypothesis? You reject it. And in this case, the null hypothesis is constant variable. How is it now, David?
This one is at 1%.
Which one is at 1%? Here, if you look at this number, 0.002, what does it mean? It means it equals 0.2%. If you just add 0. Sorry, this is only 0.2% and converted to percent. This is 0. Around 0.28%, right? And your significant level is 5% mostly, but here it's lower than 5%. That's why you reject null hypothesis, isn't it? Here this is dot, so it have to be 0 dot. Is that clear, David?
Teacher,
So if you, yep, go ahead.
Only if we accept null hypothesis, it is a homo, right?
Yep.
Okay, thank you. Understand.
If you accept, yep, if you accept null hypothesis of proof Paragon test, there is a homoskedasticity, so this standard error is correct. You don't have to do anything with this standard error, right? You take it if you accept homoskedasticity. But now there is a heteroskedasticity, so this standard error is incorrect. So you have to run regression again and put robust. Right? Questions? In theory, in fact, there are a few tests that you can test for heteroskedasticity. But the most commonly used one is this one, Bruce Paragon test. Bruce Paragon test is the commonly used test for detecting heteroskedasticity. Question, guys? Can you follow me? All right. Now let me move to the next example below. All right. Below about when I run, the price on lot size, square, I think square foot, the size of the house and the number of bedroom here. But now we no longer use price, we use lot price, right? We use lot price. Instead of using lot size, we use lot size. And now we use all these three variables using log. Previously, I told you guys that one way that researchers decided to use log rather than non-log because they want to have normal distributions, normal distribution of data. But here, if you look at this equation, when they use log, all right, and when they run Paragon test again, you see here, David, everyone, p-value now is 245, or if you use LM here is 239. So in this case, what we say here, we accept null hypothesis of constraint variant. So in this case, the standard error that produced in this below equations is already correct. You don't have to do anything. So it seems that when you use log, sometimes, not always, it also helps you to solve the issue of heteroskedasticity. All right. So in this example, when we use non-log, we found heteroskedasticity. Looking at the p-value here, right? Use only one, right? And here, when you use log, you found that p-value is no longer significant. So meaning that if you use log, somehow it can help you to avoid heteroskedasticity issue. Follow me? Questions? Yep.
About logarithm, can we use on a variable with percentage?
Normally it is not important. It is not important because normally percentage it have lower bound and upper bound, normally between 0 to 100, and that normally is not much, but sometimes there is some theory behind that, so you need to have a clear idea why you use log, right? So normally with percentage I rarely see it, but probably in your field it depends on the reading, it depends on the paper, what they want to make. Sometimes, for instance, they want to have an easy interpretation. When you want to have an easy interpretation, if both dependent and independent variable are locked, you can interpret it as elasticity, right? 1% increase in X, how much percentage increase in Y. So that is why it is easier for interpretation. It depends. But mostly, when you have 0 to 100, which is in percentage, they rarely use it. But again, as I said, the when it's sometimes it depends. If they want to have an easy interpretation, such as they interpret it in elasticity, so they want to use log.
Thank you, teacher.
Guys, can you follow me with this Paragon test? Sorry, Paragon test for heteroskedasticity. Remember, guys, I suggest you to use Paragon test to detect heteroskedasticity. After that, I will introduce you another test, but you can't just stick to one. And with Paragon test, there are two types of value, either F or LM. Don't worry, they should be the same. The result should be the same, even though the score is a little bit different. All right, don't worry. Just use Paragon test for now. Question about this, guy? How to test heteroskedasticity? Silent mean no.
Teacher, I have a question.
Go ahead.
Teacher, what if we use log and then we still face the heteroskedasticity issue, like we still reject the null hypothesis?
If that is the case again, and when we use robust standard error, you run the regression again and then add VCE robust or simply robust. If that log variable contain heteroskedasticity, again, the standard error here is wrong. The standard error here is incorrect. So you have to run a new regression using robust standard error. And then when you summarize our table, like in previous section, the note below you say robust standard error are in parentheses. Don't say standard error. Tell them robust standard error are in parentheses. All right.
Okay, like yes.
It doesn't matter if it is log or non-log. It doesn't matter if any type of model. If there is a present heteroskedasticity, meaning that you have to do something to correct standard error. All right. So let me go to the data again. All right. This data here, just to quickly introduce you again. We will get back to it later after the break. So here, if you use the data that I uploaded in the data folder, it is H price 1. You can run simply regress price, which is our dependent variable. All right. And then load size, this variable, I really don't remember it, and then number of bedroom. All right. When you run it, this is the model, and then you run this variable. State, heteroskedasticity test, right hand side, I*6. I want to report I*6. All right. And here you see the probability value 0.002 here. As you can see in here, let me change the color. All right. Here you see the p-value, but remember to look at it for most cases, null hypothesis. Null hypothesis test constant variance, so we reject null hypothesis. So here, what that say here is that now this model produce, contain heteroskedasticity. So you have to run this regression again and then add comma. You just put robust or VCE robust in the same. All right, meaning that this standard error here is incorrect now because here we reject null hypothesis. All right, that is the idea. Next, when we want to change it to log price rather than price, and then log and log, and when we run it, we test for heteroskedasticity, and now you see that there is no present heteroskedasticity in the log model. Guys, it is not always. As Muni asked, what if we found heteroskedasticity? Again, you have to correct standard error again. It doesn't mean that when you use log, there is no heteroskedasticity. No. If that is the case, they don't develop this test. All right. I hope that is clear for everyone. And my suggestions for you guys is that if you want to test heteroskedasticity, remember it's good or it's easy for you guys to use this Paragon test. Right? Use this Paragon test. Questions before we move to another test? It's just another test. Question, guys. I try, not to help much mathematical equations, but still you guys are silent.
No question, sir. No.
All right. All right, guys. Then let's move next. Earlier, we talked about Paragon test to detect heteroskedasticity. Now, I want to introduce you guys to another test. But remember, when you detect null heteroskedasticity, you don't have to use multiple tests. Use one test is enough. Right? Use one test is enough. But now I want to introduce you to another test, and I want to tell you the difference between these two tests. Remember, Paragon test simply regress your variant or sphere residual on your dependent variable of interest. That is what Paragon test did. For Y test for heteroskedasticity, it's more than what Paragon test did. For instance, we still have dependent variable, which is we still have dependent variable, which is residual sphere, all right? But this time, this Y test does not only include your independent variable. It also includes sphere term of your independent variable and interaction term of your independent variable. This is the difference between Y test and Paragon test. Paragon test only include your independent variable, but vice test include square term of your independent variable. Here we have x1, now we have x1 square, x2 we have x2 square, x3 we have x3 square as well. It also includes interaction term. x1, x2, we interact x1 and x2, we interact x2, x1 and x3, and then x2 and x3. This is the difference between vice test and Paragon test. So vice test include more variable than Paragon test. And the null hypothesis is still the same, constraint variant. But because they have so many independent variables, vice test only produce statistics. All right. So the disadvantage of this test compared to Paragon test is that it includes all square and interactions that lead to large number of estimated parameters. And when you have a small observation, it's going to be a problem. That is why I suggest you guys just to use Paragon test. And the procedure, guys, is still the same. And this is an alternative form, but that's okay. You can do it. But this is an example. When we use the last example, when we use log regression, the log price, here when we use the vice test, we still obtain homoskedasticity. The p-value is higher than significant level, right? So we only report here is the vice test for you guys using the second example, the example that we use log equation. So let me go quickly down to this here. So we regress log price, log lot size, log square feet, number of bedroom. We still obtain the same regression result, but now we don't use Paragon test. We use state im test white. This is white test, all right? And the result here is rejecting null hypothesis. Rejecting null hypothesis of earlier. You see it noted down as constraint variant, but this it say homoskedasticity. All right, constraint variant means homoskedasticity, right? So the null hypothesis is homoskedasticity, and alternative hypothesis is unrestricted heteroskedasticity. So again, we reject this null hypothesis. Question, guy? So if you compare vice test with Paragon test, vice test has a higher number of explanatory variable on variant than Paragon test. Paragon test only use x, but vice test use x square, use interact term of your independent variable. Questions?
No question, teacher.
All right, let's have a minute or 2 minutes for the other people, you guys to join me. Right. So if I don't introduce you guys to a little bit of the story behind this, it's very short. You just simply learn how to correct standard error when there is heteroskedasticity, and simply learn how to detect heteroskedasticity with Paragon test, with vice test. Again, use only one. It's up to you. But my suggestion is that you can just put Paragon test to make your life easier. Quick, you don't have to spend a lot of time to make decision why this and why that. Guy, if I am a little bit fast, just honestly tell me. Sometimes I forgot myself.
Teacher, can you explain or clarify again on why we should use Bruce Paragon rather than white test?
Oh, simple. There is no any critical main design behind that. Simply is that I just want you guys to use Paragon test, because if I understand correctly from the literature, Paragon test is the most commonly used test to detect heteroskedasticity. And secondly, if you compare between the Weiss test and Paragon test, that the disadvantages of the Weiss test that it includes your square and interaction term that lead to large number of estimator. Right? If you have small sample size and you have this large number of estimator, you will have low degree of freedom. Remember, what do we mean by degree of freedom? Number of observation minus k minus 1. In this case, if you run Paragon test, if you only have 3 independent variables, all right, estimator only 3. But now, if you use Y test, it becomes 9. 3x, 3 square term of x, 3 interaction term. Assuming that you have, for instance, 30 observation, all right? If you have 30 observation equal n equal 30, and you have number of independent variable equal 3. If you just prove Paragon test, the degree of freedom is simply 30 minus 3 minus 1, which is equal to 20, 26. But if you use Y test, it becomes 30 minus 9 minus 1. It now only have 20 degree of freedom. Mathematically explained, in simple, it disadvantage of this Y test is it include square root and interaction term. Also, I don't oftenly see Y test was used for detect heteroskedasticity in empirical paper. Mostly we use Paragon test. That is a simple answer. All right.
Thank you, Lucky.
Right. In fact, to answer many questions, I should explain more. But I'm afraid that it's gonna make you guys headache. In fact, it should be depend on your model, depend on the nature, so far and so forth. But this is your introduction. Don't go too much. So I just simply say to you guys that use Paragon test is okay. It's acceptable. Any other questions? So let me summary again. The lecture here, I start with the story. What is the consequence of heteroskedasticity? Then what is the equation for robust standard error? What is the equation for Paragon test? What is the equation for Weiss test? But in fact, in summary, we only include this lecture in 2 statements. The first statement is, if your model contains heteroskedasticity, your model produces incorrect standard error. Correct it. How to correct it? In Stata, use robust. The next statement is, how do I know that my model contains heteroskedasticity? You can either use Paragon test or Weiss test. But I suggested you guys to use the first time just use Paragon test. Otherwise, you may use 2 and sometimes results may not be the same. All right? And another idea is why you don't use this Weiss test, is that to answer many another just a simple answer, because you simply want to regress, you want to use x1, x2, and x3 only. Why in heteroskedasticity you have to include, x square and then interaction term of x1 and x2? Because in your original equation you don't include that. That is why you just use Paragon test, make your life easier. All right? So only 2 takeaway. If there is heteroskedasticity, correct it. How do you know it? Test it, use Paragon test. And how you do it? In this slide. And again, we will do it after break. The hand-on exercise. Questions before break?
Teacher, what if we correct everything and it's still like heteroskedasticity still have present? We drop variable, right? Or no?
No. Heteroskedasticity, when you test it and then you run robust, you don't have to check it again. For instance, in our earlier regressions, like this, when you already use VCE robust, this is robust standard error. That robust standard error already correct for heteroskedasticity. No more problem about heteroskedasticity. When you talk about dropping variable, it's more about multicollinearity. When there is a multicollinearity that you detect, if you remember from another lecture, you use VIF command after you run regressions. The idea is simply to probably drop one variable. But again, we also discussed that in the lecture. You have two choices. Either you have to drop one variable to address the issue of multicollinearity, but if you drop the variable to address the issue of multicollinearity, you may have an issue of omitted variable bias. We discussed that. So my suggestion during the lecture, if there is a multicollinearity, have a look at the variable. Are you sure that if you drop one of the variable, there is no omitted variable bias? If you're sure, you can drop it. Then you can address both problem of heteroskedasticity, sorry, the problem of multicollinearity and omitted variable bias. But if you drop it and it resulted omitted variable bias, it is not a good idea to drop it. All right. If we have to trade off between coefficient and robust standard error, coefficient is important. Of course, robust standard error is also important, but when you have large sample size, standard error is acceptable. When you use robust standard error, is that, do we answer your question, David?
Thank you, teacher.
Right. When you talk about dropping one variable, it's not about heteroskedasticity. It's about multicollinearity. Any other questions? All right. If there is no question, let's have our break as usual, 30 minutes. Now it is 6:48. Please return back to our group at 7:18. All right, 7:18 or 19. Right, I see you after break. Your 30-minute break start now. Hello, guys.
Hello, teacher.
All right, guys. Next, we are going to do a hand-on exercise. Today, we're going to use 3 data. But this one, you already have it another day. So for today, you have to download this H price one and wage one data. All right? Download the data first, and then we will get back to this data. I suppose you can see my share screen right now. The whole desktop. All right? We're going to use these 3 data for today exercise. This bins FP2, it was from another day. And for today is H price one and wage one data. It's basically from our lecture.
Teacher, before we start, can I ask some questions?
Okay.
For my group assignment, like I have run and I correct it to be stationary already, and I look like multi-collinearity issue also doesn't exist. Like there's all this issue already. But when I run regression, all the variable it accept the null hypothesis. So when I correct everything and it shows things like that, it's the result.
So probably something wrong with your corrections, Darwin. That is why in the message I suggested you to ignore this problem first. You mentioned about multicollinearity. You mentioned about the stationary issue. All right. So if I remember correctly, your group used time series data. Am I correct?
Correct, teacher.
Right. If I am correct, you can first try simple linear regression first. No, multiple linear regression first. Just ignore multicollinearity issue, ignore stationary issue. Because I do not look at the detail how you convert the data, how you make sure that your data is stationary. All right, for time series, we want data to be stationary. We want it to be, yes, stationary, which means it does not contain unit root. So for now, that is why I suggest your group, Darwin, to have a look at a simple linear regression first. Does it make sense to you? And that is the case, just run that set of regression, and then next week, you will learn some basic model of linear regression. We'll look at static model, which is basically multiple linear regression. We look at lag regression, and if there is stationary issue in your case, you don't have to correct it, because in our course we do not cover stationary or non-stationary issue. But I will suggest you to add trend variable next week. All right. So just run the way that you have first, and I may next week ask you to add trend variable in your regressions. Is that okay, David?
Okay, teacher, thank you.
Right, right. In fact, you are right, David. You should correct for non-stationary to be stationary. You need your variable to be stationary. But because our lecture do not cover the model that use stationary or non-stationary model, that is why I suggest you to run a simple linear regression first. Have a look if the model makes sense to you. And next week, when it comes to the time series model, please ask me more questions so that you have more idea. All right. I just afraid that when you convert the data from non-stationary to stationary, probably something wrong. One way to do it is you use first difference. All right. But let's discuss this later to be beneficial for everyone. All right.
Oh, teacher, about first difference and second difference, we use it to make it a stationary.
Right. Correct. Correct.
Okay. Thank you, teacher.
So you have a good idea. You have a good knowledge right now because you do more researching before the lecture. That's good. Ask me more questions next week. All right. For now, guys, make sure you have data in FP2, H price 1, and wage 1 in your directory folder. What we are going to do now is to do hand-on exercise. based on our today lecture, which is not this one, the heteroskedasticity, right? This one. So we start from the beginning, right? What we are going to do to start first, please open your data, and first of all, open which one data, guys. Which one data, all right? You open the data here. I already put it in my directory folder. Remember, as always, just do for. All right, I run here. I have the data H1 dataset here. All right. What we are going to do is to follow this step to produce these regressions. First of all, open the data. Which one data, everyone? As I tell some of you guys, if you look at introductory econometric textbook, in example, they always refer to data. This weight one data is from their textbook. All right. For those who are interested to look at education and weight, you can look at this data. All right. Guys, have you opened the weight one data in your data?
Open, teacher.
Right. So wait a few minutes, a few seconds for the other members to join us. Make sure you open which one data right now. All right. So what we are going to do next is to follow this. All right. We want to correct standard error. We want to use robust standard error. All right. Simply follow this far guide. So here we run not this one. All right, this one. I'm sorry. So first of all, you run. I get back to my default. Regress, log weight, education, experience, and experience where. Run it. It's just a simple multiple linear regression, right? This is the regression result without prior knowledge of heteroskedasticity. We obtain standard error. Have you obtained the same result? Race, log weight, education, experience where. By the way, guys, do you remember how to interpret the effect of education on log weight? How you interpret that? Anyone have any idea? Drop in the chat box, guys. Do you remember? How do we interpret the effect of education on weight here? Anyone remember? If you don't want to talk, drop in the chat box. How should we interpret the education on log weight here? Dependent variable is log right now. So what should we interpret?
Education increase by 1, wage increased by 9%.
By 9%.
Yes.
Good. Anyone have any other idea? What Davin said is that, all right, if education increased by 1, we don't say 1 simply, guys. Davin, we say 1 unit, right? But in this case, education here, what is a unit? Normally it is schooling in year. So you say, if education increased by 1 year, what happened to dependent? But our dependent variable here is not non-logarithm. It is in logarithm wage. What should we say? So based on Davin interpretation, you multiply coefficient by 100 and you interpret in percent, right? If what Davin said is, if education increased by 1 year of schooling, the wage will be increased by 9%. Is that correct? Remember, guys?
Teacher, excuse me, teacher. In this case, when the occasion increased by 9%, so the wage will be increased of 1%.
No, no, that's not correct, Sinh Ha. The interpretation is mainly should be education increased by one unit, and this coefficient is something that affect Y. All right, we don't say if education increased by 9 something. No, the coefficient is the effect of educations on wage. All right. So a quick corrections. Good that you mentioned it now, so that this is not confused anymore. So we will always say if education increased by 1 unit, and then you have to know what is the unit of your independent variable. Guys, that's only be the case if independent variable contain quantitative information. If qualitative information, we don't say increase by 1 unit, right? You remember that? But now the question is whether we interpret this coefficient directly to dependent variable or we interpret it by percent as what Devin said. And for saying Ha, here we already refer education increased by 1 unit. And this again, coefficient is the effect on wage. So the question is whether education increased by 1 unit, it will, for instance, we say wage increased by $0.09, or we would say like what Devin said, increase wage by 9%. That's a best way for you guys is to get back to the documents. Or now let me show you a little bit. I don't say. So you have to get back to the lecture. So we go back to our textbook. If you don't remember, get back here. Move back to our, if I remember correctly, it's something about, don't remember if that is the chapter 3. Let me quickly show you how you interpret that. There is a summary table, right? Since not everyone reply, only Sinh Ha and the Vince. So where is it? No, not here. I think that should be. I don't remember. Is the I mean I remember the interpretation. I want to refer to the reference so that you can refer it to your future interpretations. Somewhere in chapter 2 or chapter 3. Anyone have any more idea? Any different interpretation from the Vince or from Sinh Ha? There is a summary table. Where is it? If anyone can tell me, I am very pleased to hear that. I don't remember that. Wait a few minutes. I'm going to find it very soon. All right, where is it? No, this is not.
I think it's in week 5, teacher.
In week 5?
Yes.
Multi-collinear regression, but in which ones? In the inference, or it should not be in inference. It should be in estimations, or either in. Wait a minute, guy. I want to refer to the full textbook so that you can refer to it and use it in the future. No. That is not correct. Let me get back to our simple linear regression again. I don't remember where is it for the time being. I remember that there is a table that tells you what if dependent variable is log and then your independent variable is log. How should you interpret that? It takes a lot of time. My apology, everyone. Right here, table 2.3. Can you see that? Guys, look at here. So what it say here, this is the interpretation. If dependent and independent variable are both low level and level, one unit increase in x, how much it increase in y is your beta. But now our dependent variable is log, right? And our independent variable is non-log, or we call it level. So one unit increase in year, increase here you see dependent variable is percentage, but you have to multiply coefficient by 100. That's what the Win mentions. That's what the Win state interpret, right? So basically, one unit increase in education, or if education increased by 1 year, the wage multiplied by 100 and then be interpreted by percentage. All right. So always refer to table 3.3. All right. So here, what the Win interpret is correct. All right. If education increased by 1 year, the wage will increase by 9%. All right. Guys, that is not our purpose of today's exercise. Our purpose of today's exercise is about heteroskedasticity, but none of you reply. No, only a few of you, only the Win and Singha reply me. Singha, is that okay?
Yes, sir, I'm clear now. Thank you,
Okay,
sir.
good. Always refer to table 2.3 that I showed you earlier if you don't remember. All right, good. In our lecture, assuming that this table is incorrect, assuming that there is a heteroskedasticity in this model, what should we do? All right, what we should do is we have to correct the standard error. As you can see now, standard error is simply said standard error. You need to use what we call heteroskedasticity robust standard error, or in short, robust standard error. So simply, you just add VCE robust, all right? I come back to our model, to our do file, all right? And then I run the same regressions, just copy and paste, all right? Comma, VCE robust, sorry, robust. And run it, you will obtain robust standard error now, right? And you see that after you have obtained standard error, we simply have a larger standard error. T statistic is reduced, but p value is something is smaller than before, higher than before. This is the correct standard error when there is an heteroskedasticity in our model. Can you follow me? You can have a look at my do file. Or another way, guys, you don't have to run VCE robust. Simply type robust. I run here the same, but not VCE robust, but just robust. You obtain the same result, right? Either way is fine. This is what we call robust standard error. Robust standard error. This is also the same. Robust standard error. Standard error. Questions?
Robust and VCE robust same, right?
Right. It produces the same result. It's just that the way that they develop first time is they use VCE. But later on, the data is updated and modern, so we just simply use robust and also produce the same result.
Okay, sure.
All right. Again and again, you only use robust VCE robust only if your model contains heteroskedasticity. All right, contain heteroskedasticity, or what we call heteroskedastic variant. If you don't use robust standard error, we don't say your result is wrong, but the hypothesis testing or the t statistic here is incorrect. Questions?
No question, sir.
All right. Then let's move next to testing. All right. For testing, guys, to follow the lecture, in fact, we can do this data set, but I just want you to follow the lecture so that you can do it yourself next time. Now we are going to use H price 1. All right. H price 1. So I run clear, meaning that I clear existing data, and then I use this H price 1 data set. Please open H price 1 data set. Now you have this variable, a set of variables here. Right? We are going to look at this equation. Guys, if you have any problem with opening data or download data, don't forget to inform me. Talk to me or drop in this chat box. Have you opened the H price 1 data?
Open, teacher.
All right. Devin, just wait a second. Thank you for your reply. Then wait for the other member. All right. So what we are going to do now is to run regression to see the effects of 3 variables on price. And what we are going to look at is price. Here, price is the house price in 1,000 US. And then BD room, which is the number of bedroom. Lot size here, this is the size of lot in square feet. And then square feet something, this is the size of house in square feet. One is the size of lot, one is another one is the size of house. All right. You can do simply run summary. Look at this 4 variable price, the lot size, square feet, and number of bedroom. All of these variables are, sorry, it's wrong. Let's say sum or summary price. All right, square root lot size. All right. So you see the variable here for the number of bedroom is between 2 to 7. Price is in 1,000. All right. Square root here, this is the size of the house in square feet, and then size of the lot is lot size. All right. So what we are going to do next is to first, in order to use statistical test, either Paragon test or Wise test, you first need to run regression first. You have to run regression first. Immediately after regression, you run the test, right? So what I am going to do is, right, I'm back. Here is to regress price, lot size, square feet, and number of bedroom. I run this regression. This is my original regression, right? Before you run the test, right, you need to run regression first. Why? Because our test is want to know whether the model that we produce here produce heteroskedastic variant or homoskedastic variant. Have you obtained the result? All right. What we are going to do next to use the Paragon test. In Paragon test, there are 2 values of statistics. Statistic or F statistic. So after regression, you run state. This is the post estimations. State guide, and then have test. refer to heteroskedasticity test. All right, let me manually write it. E state, all right, E state, head, refer to heteroskedasticity test, head test. Comma, right hand side variable, and I want as statistics. That is the proof Paragon test using as statistics. After that, you can run. You will obtain this result. So have you obtained the result?
Obtained, sir.
Right. How about everyone else? Do you have any problems or challenge in running this Bruce Paragon test, detecting for heteroskedasticity? Please talk, guy.
Teacher, I already ran it, but it had different result. It shows 6.35.
This one, 6.35. First of all, you need to make sure that you run the same set of regressions. Have a look here whether your independent variable here is the price here, because in our regression here is going to be a little bit different. We also have log price, log lot size. Remember, if you do the same here, first you have to check dependent here, we use price. Independent here, we use lot size, square feet, and number of bedroom. Can you check that here? We should obtain the same result.
Oh, I can choose one variable.
Right, correct.
Okay.
You should have the same result. All right. So guys, you should obtain the same as statistic, and here specifically look at probability. If you look at the result, proves Paragon or test for heteroskedasticity. Hetero, which is the null hypothesis, constant variant, right? The variable that we use here is lot size, square feet, and number of bedroom. So now you see that p-value is 0.0020, lower than significant level at 1%, 2%, or 10%. So what we say here is that we reject this null hypothesis of constant variant. So what do we say? Our model here is contains heteroskedasticity. So what should we do? If there is a heteroskedasticity, what should we do? Run the same regressions, right? Run the same regressions. Wait a minute, we are outside. Run the same regression, guys, and then just as we do it earlier, robust, right? This is how we correct standard error, because we already know that our model contains heteroskedasticity. All right. Right. Here I said this is I correct for heteroskedasticity. We produce this robust standard error, right? Question, guys. Detect standard error using Proust Paragon test and creating standard error. Another way, guys, another way you can do it quickly rather than to use this. You simply run regression, all right? You run regressions and then just use this head test, heteroskedasticity test. This is also proof Paragon test, but this use no longer the F statistic. This is the LM statistic. This is also okay, right? This is also okay, but this is not a suggested one. I would suggest you to use this F statistic, right? Right. All right. Question, guys? Any questions so far?
Teacher, may you scroll to the regression result?
Here, right. This is
Yes.
non-robust, and this is the robust one. Which one do you want to look at?
The normal one in
Yes, here.
Yeah. In the degree of freedom, we run the three independent variable, but what is the residual degree of freedom? It has
What do you mean?
84. Below that.
Oh, this one?
Yes. What is it?
This is the degree of freedom of that residue. This is the degree of freedom of our model here is 84. Why it's 84 here? How many is number of our observation? 88 here, right? 88. What is number of our dependent variable? -3. K is 3. You remember degree of freedom? N minus K minus 1. What is N? 88. What is K? 1, 2, 3. What is 1? Constant. So 88 minus 4, it is 84. Either one or this one.
Thank you, teacher.
Right? So degree of freedom is N minus K minus 1. All right, guys? Any other questions? This is quickly how you detect heteroskedasticity. If there is a presence of heteroskedasticity, use robust standard error. That's it. All right. So we follow example. What if now we use log price instead of price? We use log lot size, we use log square feet. All right. So in our model here, you see, instead of price, we have log price variable, right? Instead of lot size, we have log lot size. Instead of square feet, we have log square feet. We still use number of bedroom. So now we run a new regressions with log, right? Log. Here I run regress, log price, log lot size, log square feet, number of bedroom. And then I run heteroskedasticity test using proof Paragon test again. The same command. Give me a second. Right? Did you get the same result as mine with this log regressions? So when you do log regression, you see S value and the probabilities value. What we get here is that the probability you use is around 24%. higher than 1, 5, and 10%. So we accept null hypothesis. The standard error is already correct. We don't have to correct our standard error. All right. This is Bruce Paragon test. Again, let me emphasize this. One reason that we use log, natural logarithm is, first of all, to have no more distributions. Later, you will learn that log also tells you the nonlinear relationship, but that's okay for now. But here in this example, log also can help our model to avoid heteroskedasticity issue. Any question, guys, with this Cruz Paragon test? By the way, how should we interpret the result of this log lot size on the log price? Any idea? How should we interpret this? If log lot size increased by, it affects Y by, what should we interpret this? Remember that?
Without multiply by 100, increase by 16%.
All right. So because both independent and dependent variables are in log, we can simply say it is in elasticity. If you remember, elasticity is more in percentage directly. If log lot size increased by 1%, the house price increased by 0.16%. That's what it said. Right, that's correct. But for number of bedroom, we say as earlier, if number of bedroom increased by 1 unit, by 1 room, the number, the price will be increased by 3.6%. Right, that is the interpretations. Any question about this proof Paragon test? Next, we will going to look at White's test for heteroskedasticity. All right. For White test for heteroskedasticity, we use the same regression guide as in our data in our lecture. We still use this regressions. We look at the regression of log regression. All right. All right. So you run again log regression of log price. All right. This one, I would say this is White test. Regress log price, log lot size, log square feet, number of bedroom. All right, run it. And then for White test, you write estimate im test White. This is the White test. All right, again, after you run regressions, use a state im test, comma White, specify it to be White test. Have you obtained the result as one? So normally when Proust Paragon test reject null hypothesis of constraint variant, White test also have the same result. Either they have different value or similar value, but the result normally consistent with one another. So in this White test, as you can see, White test for H0, which is null hypothesis, homoskedasticity. HA, which is the alternative hypothesis, heteroskedasticity. And here you see the probability is 38%. higher than 1, 5, and 10%. So we also reject or accept null hypothesis of, we don't say we accept, we fail to reject null hypothesis of homoskedasticity. So the model is already flat. All right, this is white text. Can you follow me, guys? Questions? This is the hand-on exercise on detecting or testing for heteroskedasticity and correcting standard error for heteroskedasticity.
So what is chi-square knowing? What is it again?
This chi-square is the LM statistic that is mentioned in the above. I don't. That's normally chi-square is a different value from statistic, but I don't want to go to detail. You simply look at the p-value here, right? This is another story that I should review it in the statistics. All right, it's similar. It's just a different way of generating a statistic call value. I just want to answer you in short here. I don't want to confuse everyone here so much. All right, is that okay?
Okay.
So simply, guys, that is why I ask you guys. I don't want you guys to be too much burning your brains. So look at p-value. Questions with our heteroskedasticity? What I am going to do next is to do a linear probability model that we covered last week, but we did not do the hand-on exercise yet. Any question, guys, about heteroskedasticity, testing, and correcting standard error?
No, sir.
All right. Thank you, hands. Guys, I assume so far that is good for every group. I don't say everyone. All right. What we are going to do next is to look at linear probability model. What is linear probability model again? We already covered it last week. When you have dependent variable, it's a dummy variable. We don't cover when your dependent variable contain multiple categories. We don't cover it in this course, right? We only talk about when your dependent variable is a dummy variable. All right. To do this, we need to use this data, everyone. The data from the past week, which is wins FP2. All right. Open this data, or follow the last week. You have to go back. You can use web. All right. Web link here. Let me copy and share it in the chat box. You can just type the link into your do file, and then you can extract the data to your Stata, load in your data to your Stata. All right. So now I load this data into my Stata. Now I got it. All right. So you can either download this data or copy the link that I share in the chat box and put it in your do file. These are the two ways that you can load the data into your Stata. This data is about the example that we mentioned last week. Let me get back to our material here. It was week 11. The data, the regression on married women participation rate. This one, label for participation rate of married women. This example. Right? Can you open the data in your data right now, either from the web, from the cloud, or from your downloaded data? Is that okay? Can you open the data right now, everyone?
Not yet, Guru. Wait, please.
All right. For those who have downloaded, you can open the data in Stata. We will talk about linear probability model in a few minutes. Does anyone have any problem with downloading or opening this data in your data? All right. So I assume that since no one's mentioned it again, so now let's start. So first of all, let's have a look at the data, everyone. In this data, there are 2, 4, 8 variables. And we are going to run regressions on using this all variable. So we have here is our I3, which is the paired labor force if the merit demands are in labor force or not. All right. K5 is the number of kids below 6 years old. K6 to 18, it is the number of kids between 6 to 18 years old. Age, which is the wife age, which is the age of merit demands in years. WC, this is WC, which is white college. 1 if the merit demands attended college. 0 if they do not obtain college degree. HC, this is the husband college. 1 if the husband obtain education or got the college degree. 0 if not. LWG, this is the log of wife's estimated wage, right? The income from wife. And the income here is the family income, exclude wife. So what we are going to do is to run regressions, except using log y estimated wage. We will run all the regression, all right? We will run the regression of the other 6 variable, K5, K6, 18, age, Y collect, husband collect, and house and family income exclude wife, all right? To see the factor that affecting the merit women participation in labor force, all right? So first of all, we can just run summary to have a look at our data, right? Summary all the variable, LFE, participation in labor force, K5, kid under 6, K6, 18, kid between 6 to 18, age of the married women, college, husband college, and family income. Run summary. So what you see here is, this is our dependent variable here is 0, 1. It is a dummy variable, right? 1 meaning the married women is in labor force. 0, it is not in labor force. All right. K5, number of kids, minimum is 0, maximum is 3. Number of kids between 0 to 18 here, between 0 to age. The age is about 30 years to 60 years. If the women is in college or not, it is also a dummy, 0, 1. If husband is it in the college or not, is 0, 1. Income here, it is in log, I believe. All right, that is why it is negative. Log 0, it becomes negative. So this is the incomes, household income. All right. So next, what we are going to do is to run what we call linear probability model. What is linear probability model again? Simply because our dependent variable is dummy. All right. So we run regress or rig, right? This dependent variable and then independent variable. Right, so regress LFP K5, K6, 18, 8, Y is collect, husband collect, and household income exclude Y estimated income. Because if the Y is not working, there is no income, right? So it's better not to include this variable. First, run this first, everyone. Have you obtained the result as mine?
Yes, sir.
All right. Does anyone have any problems with running these regressions? Remember, guys, we don't call it multiple linear regression anymore. We call it linear probability model. Right? Change your mindset because dependent variable now is a dummy. We don't call it multiple linear regression. We call it linear probability model. Guys, if you remember from lecture, I told you that, in fact, that linear probability model is not correct. You should run, in the future, you will learn logistic regressions or probit regression. But for now, that's okay. Linear probability model is also okay. All right. I hope everyone got the result. Guys, remember how you are going to interpret. How you interpret K5 on here. First of all, you look at significant variable, right? How do you interpret this K5 on this LFP? How do you interpret this? Anyone remember? How do you interpret the result for linear probability model? Anyone want to try? Either you want to drop it in the chat box. If you don't want to talk to me, try to answer yourself. All right. First of all, K5 is the quantitative or qualitative? K5 is the quantitative information, right? It is the number of kids under 5 years old. And LFP is a dummy variable. All right. So since P is 0, 0, which is significant, you say that if number of children age under 6 years old increase by 1, if the children under age 5 years old increase by 1%, it reduces the probability of married women to join labor force by 30%. All right, 30%. You can say it reduces the probability by 0.3, guys. Normally the probability, you can say it because probability is between 0 to 1, right? But if you want to say it in percent, it just simply multiply by 100. So again, if the number of children under 6 years old increased by 1%, it reduced the probability of married women in joining labor force by 0.03 or 30.32%. Is that okay? All right. Can you follow the interpretations? How about case 18? It is not insignificant. It is insignificant. P-value is bigger than significant value. How about age? If the age of married women increased by 1 year, it reduced the probability of joining labor force by 0.013, or it's about 1.3%, right? Right. That is when our independent variable is numerical variable. Now, what about WC and HC? WC is also a dummy, if you remember. The dummy, if women obtain correct degree, 0 if the married women did not obtain correct degree. So for this WC, you see, P value is significant. How we interpret it? If, sorry, not if. All right, correct. Comparing women with the correct degree to the women without correct degree, all right, the probability of joining labor force, participation in labor force is about 21% higher than women without correct degree. In other words, you could say, if women, all right, if women obtain correct degree, it increased the probability of joining labor force by 21%. Following me? Now we have both independent and dependent are both dummy variable. If women obtain correct degree, it increased probability of joining labor force by around 0.21 in probability, or 21%. Right? That's true, right, everyone? Normally for women, for married women that have correct degree, she tend to want to work rather than to stay at home. Otherwise, it is a waste of her education. Right? That is true for everyone here, right? Even in the future, you get married, you have a children, but normally if you have higher degree, you tend to want to work and support yourself rather than to depend on your, or you would say depends on someone, right? Your future spouse is just someone. No, nothing related to you. All right. So if you have higher education, you want to work rather than to stay at home. That is true. And the result here support that hypothesis. Normally, most of the case, I don't know, if your husband also obtain collect degree, they also willing to support you to join to work, right? In here in our regression, we see that if your husband, if the husband of married women obtain correct degree, it also increase the probability of joining labor force of married women. Unfortunately, it is insignificant, but it also positive. Since it is insignificant, you don't have to worry about that. Look at income. The income here is also true, right? Normally, the married women that live in the higher household income, tend not to join labor force because their family may not encourage or support her to work because they have enough financial support, right? But here we would say if this is not in law, if the income of the household increased by 1 unit, it decreased the probability of women to join labor force by around 0.006, or basically it's about 0.6%. That is the interpretation of this linear probability model. Questions? Last week we discussed about that, we interpret that, but I don't know if you guys use the lectures, but I don't write the detail. I want you guys to pay attention to the lectures.
Teacher, so when the independent variable is qualitative, we compare between the base category with the like the 0 and 1, right, teacher? But
right.
When,
so, yep.
But when the independent variable is quantitative, right? Yes, quantitative. Then we just interpret it based on the number that we have, right, teacher?
Right.
Okay,
correct. So basically, either independent or independent, if it is numerical or quantitative information, increased by 1 unit, how much it increase in Y. But if this is the qualitative information, basically dummy, you always compare to your base category. If you look at this linear probability model, we always refer to joining labor force. Why? Joining labor force equal 1. 0 is not joining labor force. All right? Because the probability, normally when you say probability of having something, not probably not having something, right? So in this dependent variable, 1 is joining labor force, 0 is not joining labor force. That is why we always say the probability of joining labor force. It's specifically depending on which is number 1. Your dependent variable here, what is number 1? If your dependent variable is 1 equal not joining labor force, you would say it increase or decrease probability of not joining labor force. All right, that is a good question from Chimay. So let me stress this. With this linear probability, you have to look at the value that is equal 1. When your independent variable is dummy, you always compare 1 with 0. But when it comes to dependent variable, you always interpret probability that is get closer to 1. And what is that 1 mean? In our example here, 1 is joining labor force. If 1 is not joining labor force, we say the probability of not joining labor force. All right, it depends on the 1 value. Good. All right, that is basically just a recall from last week class only, guys. But if you remember, last week I also told you that linear probability model have 1 problem. The problem here is that linear probability produce large standard error. Or probably most of the case, linear probability model produce heteroskedastic variant. So if that is the case, let's run heteroskedasticity test. You can run as our earlier estate head test, right hand side, I star 6. All right. So I see it of course contains heteroskedasticity. Right? It contains heteroskedasticity. Or you can simply run head test as well. That's okay. It's the same. Oh, sorry, run this again. That is incorrect. All right, you should better do this one. So if it contains heteroskedasticity, what should you do? Just add robust. All right, add robust. That's correct. Right, that's correct. Question, guys, about interpretation of linear probability models and our heteroskedasticity test or correction today. Questions And today is the end of econometrics model for cross-sectional data. Next week, we look at time series. The following week, we look at panel data. Question, guys? May I ask, can you please reply to me? If your group use time series, if any group use time series, can you please write your group down in the chat box here? I know the Win group use time series. I want to know how many group use time series. Can you drop in the message? The Win, you can just write your group here. Any group use time series? Group 1. Any other group use time series, guys? Except group 1. Any other group use time series? Yes or no? Group 5 as well. All right. So group 1 and group 5. You can ask me more questions next week. But again, next week we only cover basic model, not co-integration test, not co-integration model, Targon test, not that advanced topics. All right. Our course is only introduction or very basic applied econometric model. Any other group? We have group 1 and group 5. So we have SWOT group and we have Darwin group. How about panel data? Any group use panel data?
Group 2 like.
All right, group 2. Any other group than group 2?
Group 4 like.
All right. So group 2 and group 4, we will cover panel data on week 14. Guys, my apologize, but we don't have choice. You remember that you have to submit term or group assignment on 31st July, right? A week after your final exam. I have no choice. I have to submit your score, right? So you guys can start running a simple regression as you have. And when it comes to time series next week, I will tell you a few techniques that you can incorporate more. And also, for those who going to apply panel data, I will tell you a little bit more about that. And it's simply you just add, type of independent variable into your model. All right, don't worry. Basically, we apply multiple linear regression and we add more and more. Don't wait, guys. Just first of all, write introduction, literature review, methodology, and then explain us why you include your independent variable of other independent variable. All right. Thank you, everyone. So far we have 2 groups using time series, 2 groups using panel data, and probably 3 groups using cross-sectional data, because totally we have 7 groups. That is a good balance. All right, that is all for today, guys. Happy New Year. My apology, I have no choice, but you also have a quiz this week. But I'm going to extend more deadline so that you can enjoy a little bit of your new year. So happy New Year, stay safe and take care. See you next year, guys.
Yes, sir. Goodbye, sir.
Yes, sir.
See you
Goodbye.
next year, teacher.
Bye bye, everyone. Stay safe.
Happy New Year.
Happy New Year.